Hello, welcome to The Naked Scientist with me, Dominic Ford, and also with Hannah Critchlow. Hello, Hannah.
Hello, and this week, how anorexia and autism might be linked. The spacecraft which is mapping out the structure of our galaxy. And the flashes of radiation from space that could tell us what happens when stars collide.
If you'd like to get in touch, email chris@thenakedscientist.com, tweet @nakedscientists, or you can find us on Facebook.
The Naked Scientist podcast is powered by ukfast.co.uk.
A little later in the second part of the show, I'll be talking to the astronomers who call themselves astroarchaeologists as they try to find out where the stars of our galaxy came from. But first, it's time to take a look at what's been making the science headlines this week. Hannah, a study has found a link between anorexia and autism.
So this is a study that's been published by a group of Cambridge researchers based at the Autism Research Centre. So Simon Baron-Cohen, who's director and professor of that unit, has been looking at anorexia, which actually affects 1 in 10 people in the UK. So it's the food disorder where people might starve themselves, and it can actually, in 30% of cases, lead to death because of clinical conditions that may, for example, cause organ failure. So very little is known about the biological basis of anorexia. But Simon was interested in some of the facets of anorexia, so this compulsion to control what you're eating and also to really kind of control and regime different aspects of your life. And he thought that might be similar to autism, which is a typically very male syndrome. So he analysed 66 adolescent girls aged between 12 and 18 who had been diagnosed with anorexia, but without a diagnosis of autism. And he looked at different aspects of their behaviour using different paradigms called the autism spectrum quotient and also the systemising quotient and their empathy quotient. So this is basically just asking them to report on different aspects of their behaviour. So, for example, how much do they systemise different aspects of their life, and also how much do they feel and respond to other people in their environment. So it's quite a subjective analysis. And he found that there was huge similarities between girls with anorexia and boys and people that had been diagnosed with autism. Now, this is really interesting because the majority of people that are typically diagnosed with autism are male. So possibly the people with anorexia have a certain degree of autism, and this could affect the way that they're being treated in terms of therapy.
Now, autism is a spectrum of conditions going right from quite mild cases to really severe cases where children can't even speak. Is Baron-Cohen talking here about severe autism or mild cases?
So yeah, as you mentioned, autism can involve a triad of impairment. So that's social interaction, problems with social interaction, communication, and also imagination. And there's a big spectrum of severity that these triad of impairments can actually take in a person with autism. But Simon Baron-Cohen is really looking at the mild end of autism and comparing them with people with anorexia. And something that people commonly associate with autism is this systemising, so kind of controlling play. So, for example, playing with train tracks and putting things in a particular order. And that's something that you also see with anorexia, kind of controlling the meals, the food that they eat. So there's a commonality there between the two disorders. And realising that and understanding that may lead to new treatments for girls and males with anorexia.
Well, let's hope so. Thanks, Hannah. Now, a paper which really caught my eye came out in the Journal of Climate this week, looking at the environmental impact of chlorofluorocarbons, or CFCs. Now, if you were following the news about 25 years ago, you may remember hearing quite a lot about the damaging effect that CFCs have on a layer of the atmosphere called the ozone layer, which is a layer of the atmosphere in the stratosphere which is opaque to the sun's ultraviolet radiation. And it means that we on the surface of the Earth were exposed to much less of this damaging radiation, so it makes it possible to go sunbathing without getting sunburned, and potentially in the past might actually have made life possible by meaning that complex chemistry that's needed for life was able to occur without being broken apart by those ultraviolet rays.
And I remember when I was a child that the refrigerators, suddenly they weren't allowed to emit the CFCs that were damaging the ozone layer. There was a big call to make sure that refrigerators complied with new CFC legislation.
That's right. What happened in the 1980s was that people realised that CFCs were used as a refrigerant in fridges in people's homes, And in 1987, the Montreal Treaty banned the use of those because they had this damaging environmental impact. That was ratified by 200 countries. And although it's taken a very long time for CFCs that had already been emitted into the atmosphere to break down, now this is often held up as being a great triumph of international legislation in solving environmental problems. But what this paper in the journal Climate is saying this week is that CFCs are also really very strong greenhouse gases. Now, we hear about CO2, carbon dioxide, and the effect that that has in causing global warming. But CFCs are actually 10,000 times more powerful as a greenhouse gas than CO2. And so what this paper is saying is that because we had this spike of CFCs in the atmosphere in the 1980s, that was causing strong greenhouse effect historically. And over the past 20 years or so, that's tailed off. So in fact, the global warming that may have been caused by carbon dioxide in the last 20 years, we may not have seen the effect of that in full because it's been offset by this diminishment in the number of CFCs in the atmosphere. So the argument is really that we mustn't just look at carbon dioxide, we need to look at the full suite of molecules that can cause global warming to really understand the effect that these gases can have.
So there's no cause to celebrate yet about decreasing CO2 levels because actually we're measuring CFC effects on global warming.
That's right. I mean, in the 1980s, we had this wonderful success with the Montreal Treaty that really does seem to have solved the problem with CFCs. We hadn't had a similar treaty with carbon dioxide. The Kyoto Protocol was not ratified in the end. And the data is extremely complicated to analyse because there's all of these different molecules all causing the greenhouse effect, and it's not just carbon dioxide.
Thanks, Dominic. In just a moment, we'll be joined by Daniel Johnson from Chemistry World magazine to look at some more news stories. But first, this week, the world's first lab-grown beef burger was cooked and eaten in London. But how was it made? And why is it important? Here's Ginny Smith and Dave Ansell with this week's Quickfire Science.
By the year 2050, the world's growing population means that demand for meat will have more than doubled, but we're currently at capacity producing meat in the traditional way.
70% of the world's farmland is used to feed livestock. Lab-grown meat would free up some of this land to grow crops to feed humans directly.
Livestock account for nearly 20% of greenhouse gas emissions, more than all forms of transport put together, because they produce such large amounts of methane.
Meat has a carbon footprint at the checkout of about 17 kilos of carbon dioxide equivalent per kilogram. Cultured meat would be a lot less.
To make the artificial burger, scientists extracted a special kind of stem cell from the muscle of cows. These satellite cells are the same cells that help your muscles heal themselves when they're damaged.
These cells are then grown in a nutrient-rich medium. They multiply many times, so one cell can become many millions.
They are then attached to a scaffold and stretched to increase their size, just like an animal doing exercise.
Currently, the growing medium is derived from cow blood. The hope is that in the long run, plant or microorganism-based mediums will replace it.
To prepare the burger, the tiny strips of muscle were minced, seasoned and shaped.
Beetroot juice was then added for colouring, as there's no blood in a cultured burger.
Taste testers said that the burger had a meaty texture, but was a little bland in taste.
Scientists think that cultured burgers could be on our shelves within 20 years.
In theory, burgers can be made from any animal that has these kind of stem cells, so we could even be eating penguin or lion burgers in the future.
Hopefully they'll be cheaper than the $330,000 which this burger cost.
Ginny Smith and Dave Ansell. Gamma-ray bursts are intense flashes of radiation that appear in the night sky, but often fade again within a few seconds. Even though they were first seen over 40 years ago, there's still a hot debate among astronomers as to what causes them. But writing in Nature this week, Professor Neil Tanvir from the University of Leicester thinks he's found strong evidence that at least some bursts are triggered by collisions between neutron stars or black holes.
So, gamma-ray bursts were discovered in the 1960s, in fact, by military satellites which had been put into orbit to look for clandestine nuclear explosions which might be being conducted in space. And instead of seeing any of those, they detected flashes of gamma rays, high-energy radiation, coming from somewhere, as far as they knew, beyond the solar system. What we have subsequently found out about them is that they're coming, in fact, from other galaxies, And it seems that there are a number of different kinds of very high energy, powerful mechanisms which can give rise to these flashes of gamma rays.
And how are we going about observing them? Is this basically Geiger counters in space?
That's a pretty good description, actually. So the light in the form of these gamma rays, because they're high energy kinds of radiation, the photons of light, the little particles of light, act really more or less like particles that you might get off a radioactive substance. And so if you put a detector on a spacecraft to detect these things, then indeed they detect each individual photon as they arrive. Now, the tricky thing with that kind of technology, of course, is trying to tell where the gamma rays are coming from, because you don't tend to get very good directional information. You tend to just sort of register that a photon has arrived. So there has to be a whole sort of sequence of trying to use other telescopes to refine the positions until eventually we nail the exact location of each gamma ray burst that we're interested in.
In Nature this week, you were talking about observations of one particular gamma ray burst that you saw back in June. And what was surprising about that, I gather, was that it faded so very quickly after it initially flared up. What was the surprise there for you?
This was a so-called short-duration gamma ray burst. One of the things we've learned after all these decades of research is that gamma ray bursts come in a number of different types, which we believe have really quite different origins, even though they look rather similar to each other. And so the short-duration bursts, the initial flash of gamma rays only lasts probably less than a second, and that was the case with this one that happened in June. Then after that, although it was quite a bright burst, it did fade very rapidly. So following the initial flash of gamma rays, what we tend to see with all gamma ray bursts is a slowly declining sort of ember of light that we call the afterglow, and we see that actually in different kinds of light, including optical and infrared and radio and X-rays, or basically the whole electromagnetic spectrum. In this case, the afterglow faded away apparently very quickly, and that's not too surprising. It's within the range of behavior that we often see. But what was special was that we observed the location of the gamma ray burst again after about 9 days with the Hubble Space Telescope. And given how fast the afterglow had been fading, we, in a sense, expected not to see anything at that point. But in fact, in the infrared pictures we took with the Hubble, we did see some light still there. And of course, we had anticipated this might be the case because people had speculated that the process that produces the short-duration gamma ray bursts might also produce a sort of long-lived radioactive afterglow as well, in addition to the normal afterglow, something that we call a kilonova.
So how much do we know about what's actually causing these flashes in the sky?
The gamma ray bursts that we see have, as I say, a number of different subcategories, and the ones that we see most often are what we call long-duration gamma ray bursts, and they seem to be produced by some kind of core collapse supernova. Now, what that is a massive star at the end of its life. It runs out of fuel, and so gravity just starts to work on it, and in a very short space of time, the whole thing collapses. And it seems that in the process of doing that, in some cases, it produces a jet of material that, as the star is collapsing, this jet thrusts its way out at extraordinary velocities, very close to the speed of light. And if we happen to be looking down the axis of that jet, then we see this flash, and that is your long-duration gamma ray burst. Now, in the case of the short-duration gamma ray bursts that we're talking about now, the mechanism we think is quite different. And there we think, that, again, we do have a jet, but it's created by the coalescence, the merging of two so-called neutron stars. So neutron stars are incredibly dense objects. In fact, they're formed as the remnants of other kinds of supernova explosion. And with a neutron star, you have essentially something like the mass of the sun compressed into a ball about the size of a town, just a few miles across, that is to say. So you've got an incredibly dense object, the densest objects we know of in the universe apart from black holes. And the idea is that if you have two neutron stars in orbit around each other, then their orbits gradually decay until eventually the two things crash into each other. And that can release an enormous amount of energy, and again, by mechanisms that we really don't understand well at all, it seems that that can produce a super fast jet of material, producing, in this case, a short-duration gamma ray burst.
So is the idea that this gamma-ray burst has a very short duration because you've got two very compact objects, they're merging very quickly, perhaps forming a black hole, which is very rapidly absorbing any material that might form an afterglow?
That's more or less exactly right, yes. So the natural timescales for that final sort of merging event is really very short, much less than a second, in fact. And so the whole process, the energy release happens really quickly, and so that then seems plausible that results in the short duration flash. The extra ingredient that really has come out of the new observations is this kilonova light, and what that is thought to be produced by is that as these two neutron stars are undergoing their final death spiral as they come in towards each other, a certain amount of the material of them is thrown out into space, is sort of ripped off each of the stars, thrown out into space, and because it's a super dense form of matter, once it's away from the neutron star itself, this fairly small percentage of the total mass of the star, but once it's ripped out of the neutron star, it expands very rapidly and forms this sort of radioactive ball of material. And it's the radioactivity from that material that was thrown out that gives rise, we believe, to the later time emission after 9 days or so. One of the really interesting possibilities that's opened up by the discovery of this kilonova is there's been a long-standing mystery as to the origin of certain elements in the universe, particularly what we call heavy elements, ones with big, heavy atoms. And that includes certain very well-known familiar elements such as gold and platinum. And those are elements which we haven't really got an explanation for why they exist in the universe. And it's long been thought that they might be made in supernovae. On the other hand, that turns out to be quite difficult, whereas merging neutron stars of the type that I've described look exactly the sort of place where such elements should be made in abundance. So it may be that all of the, say, the gold in your jewelry had its origin in an event like this that predated the formation of the solar system somewhere nearby in our galaxy, where two neutron stars merged, sprayed a quantity of these heavier elements out into the gas clouds of the Milky Way, which then subsequently collapsed and formed the solar system and the Earth and everything that we see today.
My thanks to Neil Tanvier from the University of Leicester.
You're listening to The Naked Scientists with Dominic Ford and with me, Hannah Critchlow. Now, we're joined by Daniel Johnson from Chemistry World magazine. Daniel, what's caught your eye this week?
So dieters could soon be able to monitor how much fat they are burning off, thanks to a portable breathalyzer invented by Japanese researchers.
Oh, that's fabulous. So I could monitor exactly how fat I might be in the future. How portable is this device?
It's about the size of a cigarette packet, and it works on some really clever chemistry. Basically, before, the only way of monitoring this was to use big gas chromatographs or huge mass spectrometers. Now they managed to pack all this science down using semiconductor gas sensors into something the size of a cigarette packet.
So rather than stepping on the scales, I could quickly exhale a breath of air and then monitor exactly how much fat I'm burning and therefore change the way that I'm eating?
Yeah, I mean, obviously it depends on how you use it. But what it does is it monitors the level of acetone. Now, acetone is a byproduct of the breaking down of fat in the body. And when you break down fat, you get this acetone in the blood that comes up through the lungs to your breath. So by taking a puff on this cigarette packet-sized breathalyzer, you can work out how much acetone is in your breath and therefore how much fat you're burning off.
So how have they made this new machine so compact? So previously you mentioned that you had to have this massive machine that was reading all these graphs. So what's changed in technology now?
It's using a different technique, basically. So before, to analyse breath, they would use a gas chromatograph or a mass spectrometer, which are very big, bulky machines. Now they're using two semiconductor gas sensors. So one's based on platinum-doped tungsten oxide, and one's made from tin oxide. Now, one is sensitive to the acetone in the breath, and the other is sensitive to other volatiles, such as ethanol and other things in the breath which could be coming out. Basically, how it works is the gas absorbs to the surface and modifies the conductivity. So less or more electricity is going through this semiconductor, and then that reads out as to the levels of acetone.
Could this have other clinical applications? So, for example, not just for those people that want to monitor how much fat they're metabolising for sport reasons or for dieting reasons, but also for people that have got diabetes?
Yeah, that's true. Acetone is also produced by people with diabetes, so this device could allow people to control their sugar levels.
In a very quick, easy way, rather than having to prick their finger and monitor their blood levels, they could literally just puff into this machine.
So this device is not yet commercially available, but Sugiyoshi Toyuka and his colleagues in Yokosuka hope that it could be on the market soon.
Daniel, thank you very much. That was Daniel Johnson from Chemistry World magazine. Now, Hannah, I hear toilets have been on your mind this week.
Toilets are always on my mind, Dominic, and as they are on everybody's mind. Everybody uses a toilet every day, I would assume. Now, the Japanese company Lixil have produced a particular toilet called the Satis toilet, which is very satisfactory for its customers usually. Now, it's got a range of different applications for this toilet and different kind of modularities. So, for example, you can press a button and some nice soothing music will come out as you relax and do your business. Or you can even use different functionalities. So, for example, you can have a deep cleanser or a more relaxing light cleanser in your bidet functionality of your toilet. Now, these Satis toilets actually retail for £3,800. That's about $5,500. And they're just available in Japan. Now,
But there's a problem, I gather.
There is a problem, and this has been reported on the BBC News recently. So the Japanese love their technology, and usually you can actually automate all of these different music, fragrance releasing and cleansing programs within your Satis toilet just using your smartphone app. So at a swipe of a button, you can turn certain things on or off as you do your business. Now, unfortunately, the pre-programmed security preset for this application is 0000, and the majority of customers haven't changed that preset, which means that neighbours have been going in and causing flushing and inspirational water release in the bidet system for their unexpectant neighbours whilst they're sitting on the toilet or doing other business or anything. So basically, the toilets are being controlled by hackers.
Could be quite a surprise at the wrong moment, I guess.
Exactly, it could be a surprise at the wrong moment. So not a great thing. This story is quite entertaining in some ways, but I think what it really highlights is that, for example, in telephone hacking, so this has been happening in the last couple of years, that there's been journalists that have been able to hack into people's telephones, and that's for the same reason, that there's this preset security code that the majority of people don't change. And it's important that people have high security passcodes for banking, for example, or telephones, and then maybe low security passwords for their toilet facilities. And don't just use your date of birth or something that could be guessed from anyone that gets information on lifestyle questionnaires, for example, or from your local supermarket, but try to use more complicated and less obvious security passcodes.
We're all told when we're picking passwords for computers or PIN numbers for the bank that we need a very secure code. How common is it for these systems to be hacked by insecure codes?
It really easily can happen to people. And this isn't the first time that this particular thing has happened with this kind of preset 0000 security code. So in the 1960s, apparently there's been various reports that the USA set the unlock code for their missiles, their nuclear missiles, as 4 times zeros in order to prevent slowing down release of nuclear weapons if they were suddenly attacked. Now, fortunately, they weren't hacked. So this kind of thing can happen, and just be careful, really.
And I guess there's also a responsibility there for companies like banks to make sure that we're using secure codes. Thanks, Hannah. And you can find out more information, including references to the papers we discussed, on our website at thenakedscientist.com/news.
It's time now to have a sort through the Naked Scientist mailbag and to answer some of your questions. Dominic, we've got a question here that you might be able to help with. We've all seen mugs that reveal a secret picture when a hot drink is poured into them. But Tad Davison got in touch. He wants to know how these temperature-sensitive paints actually work.
I think the mugs that Tad is thinking of, they tend to be black at one temperature, and then underneath that black ink, they've got a picture which is revealed at certain temperatures when that black ink becomes transparent. And the way that black ink works, it's a black dye which is mixed with crystals of a salt, which is either very acidic or very alkaline. And that paint is actually pH sensitive. It's sensitive to whether the environment is acid or alkali. And as the temperature changes, that material melts and it mixes with the dye. And that actually changes the optical properties of that dye and change it from being very opaque, black paint, to being completely transparent. So it's all governed by the melting temperature of these crystals that you have mixed in with that dye that change the pH of the environment very radically at a particular temperature. And they mean that when the mug is hot, the dye is black, you can't see the picture. And then as you drink your tea, you get down the mug cools down and the picture is revealed from the top as you get down your mug of tea.
Ah, that explains exactly how the mug that I have at home works like that. And it's been working for years. So obviously this particular paint keeps on going with this melting temperature pH change thing.
Yes, absolutely. You've got these crystals in there and they can change between the liquid state and the solid state mixed in with that dye many, many times. And that mug will carry on changing as many times as you want it to. So I hope that answers your question, Tad. Now, Hannah, we've had a question come in from John Bondi, who says that his feet smell like cheesy corn chips. I think I could probably think of some ruder things to say about my own feet, but what is it that makes feet smell so bad?
Well, my feet smell of roses, actually, Dominic, and I think everybody in the office will agree. But why is it that your feet and Tad's feet smell so bad? Well, it's due to this little bacteria called brevibacteria, which are also used to ripen or mature certain types of cheeses. These brevibacteria are found on human skin and in a normal kind of way. And they release, when they're living in excess, they release this little chemical called S-methylthioesters. You may have even noticed that when you've eaten asparagus, that your wee smells funny as well. And that's because of the release of this chemical called S-methylthioesters. And it smells very pungent. So the cheese smells cheesy because of this brevibacteria releasing this S-methylthioesters as part of their normal metabolism. There's brevibacteria also on our feet, on our skin usually, and kind of the hot weather at the moment is causing an outburst of this brevibacterium, kind of a party on your feet, and they're releasing this chemical compound which smells of cheesy corn chips, as Tad says.
And I guess your feet are underneath socks and shoes, and so that sweat isn't drying out, so it's a perfect environment for these bacteria.
Exactly, yeah.
Thanks, Hannah. And if you want to get in touch, you can email chris@thenakedscientist.com, you can tweet @nakedscientists, or you can find us on Facebook.
You're listening to The Naked Scientists with Dominic Ford and with me, Hannah Critchlow.
Earlier in the summer, I travelled to the National Astronomy Meeting in Scotland, and one of the areas of research that impressed me most was how much we've learnt in recent years about planets circling around stars other than our own sun. It's 20 years since astronomers found the first direct evidence that many of the stars of the night sky have planets around them, but until recently we've known very little about what these worlds might be like. Using a technique called transmission spectroscopy, though, astronomers are now starting to glean some clues about what the atmospheres of these planets are made of. I caught up with Catherine Hewitson from the University of Exeter, and as she explained, the technique relies on waiting for planets to pass in front of their host stars, and then studying the light that's filtered through their atmospheres.
We're using a technique called transmission spectroscopy, which has been in use for about 10 years or so. So what it does is, when you see the planet pass in front of the star, like the recent transit of Venus, you can actually see the starlight be filtered through the atmosphere, and characteristic absorption lines of specific elements and molecules are imprinted on the filtered spectrum. So we use that to look for different species in the atmosphere of these planets.
So essentially by seeing what colours of light are passing through and being absorbed by the atmosphere of the planet, you can start to work out what that atmosphere is made of.
Yes, that's right. Essentially, we know what we expect to see, and then we look for absorption in these particular wavelengths that tell us whether those compounds are present in the atmosphere.
I guess given that planets are much smaller than stars in general, the diminishment of light that you see when a planet transits a star is quite small. It must be really incredibly difficult to get a spectrum of that light that's being absorbed.
Yeah, so we're looking at Jupiter-sized planets. Well, we're looking at hot Jupiter, so they tend to be a little bit bigger than Jupiter, a bit puffy, and they're very close to the star, so that's why we see quite a large signal. So that's why we're not able to look at Earth-like planets yet, so we're still developing the technique to be able to do that. So what we look for is we try to pick targets or planets which are very large, which are orbiting stars which are quite small, so that the light dimming when the planet goes in front of the star is large.
Because these planets are puffy, as you put it, I guess there's a lot more atmosphere there to absorb the light, whereas the Earth's atmosphere is quite a thin layer on its surface.
Yeah, so because they're very close to the star, they get heated, so they increase their size. So for that reason, the features that we see are quite large. Essentially, the atmosphere is inflated.
What instruments are you using to make these measurements?
We're using the Hubble Space Telescope, and we're using spectrometers from the optical to the near-infrared.
I guess the molecule that everyone's interested in is water, because that's obviously the molecule that's needed for life. Have you found any evidence of that?
Well, we have found evidence of water as steam because this planet's so hot, so it's not going to be liquid water, but we have seen a water feature. So that's interesting again because we have seen the feature that we expect, whereas in previous planets, observations have shown that the feature is muted. It's like the planet is covered in clouds and you only see part of the feature. So it's interesting to see that in this planet we actually see the feature we expect. So there's a surprising diversity in the planets that I've studied so far, which is the reason we're doing a survey, to try and understand whether planets are different and why.
We've also got Hannah Wakeford here from the University of Exeter. Hannah, what else do we know about the environments of these planets?
So these are truly strange worlds. They're actually tidally locked to their star, which means that one face of the planet is continuously facing the heat, the irradiation from that star. And that means that the day side of that planet is really very, very hot, up to about 1,500 degrees Kelvin. And what we're actually looking at through transmission spectroscopy is the limb, the kind of edge of atmosphere around the side, kind of the bridge between the day side and the night side of that planet. So we're really also looking at the different temperature ranges that we're getting between those two. And these water features that we're seeing are actually slightly cooler than what has been measured for the day side of these planets, which is another really, really interesting result, seeing how the winds, how the different environments on those planets are transporting that heat from the day side to the cold night side of them.
So it's fascinating how much we're learning about these exoplanets beyond just their masses, their sizes. We're really starting to learn what these might be like as worlds. But these aren't very Earth-like worlds. You've hinted that you want to move this technique to something that's a bit more similar to our own planet. How much more difficult is that going to be?
Yeah, you're right. These are really not hospitable worlds. You wouldn't want to go there for a holiday. So to move that technique forward a bit, we really need to develop the technology a lot more. But what we're doing is really kind of laying the foundation for what we understand about looking at these molecules, looking at these fingerprints. And if we can understand them in something as big as these hot Jupiters, where the signatures should be really very clear because the atmosphere is so extended, we can really refine the techniques right down to the point where we can confidently say when we've found these other planets and we've got better instruments to look at them, we know what that feature is. We have evidence from previous studies that we know what we're looking for, and we've got it right here.
I guess the molecules that everyone is interested in are molecules like oxygen, which are biotracers of life. How far away are we from detecting those, do you think?
Oxygen's a particularly difficult one, and that's difficult because of the wavelength ranges it lies in and the intensity of the feature. And due to the intensity of the feature, it's quite small compared to other molecules. It's going to be quite difficult to find oxygen itself. But what we can look for is an imbalance in these atmospheres. So where is there being CO2 or other molecules like water? Where is there more methane? And is there an imbalance from what we would expect from these worlds? And that would kind of be indicative of something that is producing these different molecules rather than it occurring naturally in nature.
Now, Catherine, you've been using the Hubble Space Telescope for these observations. I guess to move this further, are you going to have to use purpose-built observatories?
Yeah, so hopefully James Webb will be flying soon, and that will be specifically looking more in the infrared and the near-infrared, which is where we'd expect to see features such as water and methane. That should hopefully really take over.
Hannah, there has been talk of purpose-built observatories for looking at the spectra of planets. I'm thinking of Darwin in particular. Does it look like any of those missions are actually going to fly anytime soon?
So unfortunately, Darwin is dead. It's not around. We're not flying that mission. But there's always talks, there's proposals every few years where you can put forward these different telescope ideas. And it's really important that we go into space for these. So that means that there's that higher cost and that higher risk with it. So yes, there are things in the works. But of course, the space mission proposals are years and years in the future. It took from 1984 to 2009 to get Kepler up. So watch this space. We'll definitely have something.
That was Hannah Wakeford of the University of Exeter, and we also heard from her colleague, Catherine Hewitson. We have growing evidence that many of the stars of the night sky have planets circling around them, but where did the stars themselves come from? Our galaxy, the Milky Way, is a grouping of around 100 billion stars, and all the brightest stars in the night sky are part of this family. But when and where did the Milky Way's stars form? The first step to answering that question is to know how they're distributed through space. And Lennart Lindegren from the Lund Observatory in Sweden is working on a new space telescope that will map out the galaxy.
Gaia is a satellite designed to survey about 1 billion stars in our galaxy, and one of the main results from it will be distance determinations to many of these stars, so that we get a truly three-dimensional map of our galaxy.
The problem astronomers face is that while they can measure the positions of stars on the night sky very accurately, it's much more difficult to know how far away they are. The technique Gaia scientists are using relies on the Earth's annual rotation around the Sun. Just like nodding your head from side to side, this makes it possible to judge the distances to stars by how much they appear to shift from side to side over the course of the year, as Lennart's colleague David Hobbs explains.
So basically the Earth just goes around the Sun once every year, and our satellite is somewhere around the Earth, of course. And by looking at nearby stars, then you see they're in one position in July, and then if you look at them in January, you see they've shifted to another position. And if you actually do that, and you can do it in nice video plots, you see that it traces out a nice oval on the sky. And then the angle of that oval gives you the parallax measurement, which you can convert then into a distance with a simple formula.
So over the 5 years that Gaia will be working, the stars will be seen to wobble back and forth by a tiny amount depending on their distance. The nearer the star is, the bigger is this wobble. So by measuring this small angle, we can get the distance to the stars.
So these stars are nodding back and forth in the sky. I guess that motion must be very small given how distant these stars are from us.
Yeah, when we show videos of this wobbling, of course, we exaggerate it by a factor of 100,000 or something like that. And that's the reason why you need a very highly precise satellite to do these measurements.
The technique of using the parallaxes of stars to determine their distances has a long history in Sweden and Denmark. The idea was pioneered over 400 years ago by Danish astronomer Tycho Brahe, who proved that a supernova he saw in 1572 was an astronomical object rather than a weather phenomenon in the Earth's atmosphere, as other astronomers believed at the time.
Yes, that is right. He used that method to prove that the new star, the Stella Nova, which was discovered in 1572, was actually further away than the moon, which was a revolutionary discovery at that time. So now we are using this method since 200 years to measure distances to stars, which is of course much more difficult because since the stars are more distant than the moon, for example, the parallax will become very small. And when we want to measure distances to stars in the other end of the galaxy, for example, these stars are very, very distant, so the parallax becomes very small, and therefore it is difficult to measure, which is why we can't do it until now.
So Tycho was doing this with comets back in 1572. When were we first able to measure the parallax of a star?
The first really successful or convincing measurement of a stellar parallax was made by Friedrich Wilhelm Bessel in 1838. He was working in Königsberg in Germany, and he measured the distance to the star number 61 in the constellation Cygnus. That was a real breakthrough in the history of astronomy because astronomers had tried to measure parallax for centuries, and this was the first convincing detection of the parallax.
What's Gaia adding to that? I guess by being in space you haven't got the distortion of the Earth's atmosphere.
Yes, that's right. That's very important. The atmosphere has been an obstacle for accurate parallax measurement until 1989, when the European Space Agency launched the Hipparcos satellite, which was the first satellite designed to measure parallaxes from space. And it did that very well, with an accuracy of about 1,000th of an arcsecond. but only for about 100,000 stars, and only stars rather close to the Sun. With Gaia, we want to measure many more stars and many more distant stars, and therefore we need much more accurate measurements.
Gaia is 100 to 1,000 times more accurate than Hipparchus, just because of the new instrumentation. But the measurement principle is basically the same. If you think of Hipparchus and you plot what kind of scale Hipparchus could see for a solar type star, for example, on top of the galaxy, then you will see that Hipparchus could only see very locally. It's a little dot on the galaxy, basically. It certainly wouldn't be much bigger than just sticking your pen on a piece of paper. But if you take Gaia, then you can see that the distance scales that Gaia can probe for the same kind of star is very far out. For solar-like stars, Gaia can probably see out about 8 kiloparsecs with an accuracy of 10 to 20%. And that in astrometry is considered to be very good. But then for very bright stars, Gaia can see right the way across the galaxy.
We often hear about exoplanets being discovered by their gravitational pull, causing stars to wobble back and forth. I guess there are a lot of other phenomena that you're having to distinguish this wobble from.
Yeah, of course. So what we do is we build models of how the light should enter the telescope, basically. You have to take into account a great many things. Of course, the finite speed of light, for example, this is known as the Romer correction, has to be put into the time measurements even. Then you have the parallax wobble, as I mentioned, but also you have the light deflection in the solar system. So you have to have a model of general relativity, which is an extremely accurate model. It must be more accurate than the final precision of Gaia. So we have to have a micro-arcsecond relativity model.
So the issue there is that the bodies in the solar system bend light because of their gravitational fields.
Yeah, sure. And you have to take this into account. And of course, the sun, for example, at 90 degrees to the sun, you're still getting 4,000 microarcsecond light bending. So it's an enormous effect. So you have to take the sun's light deflection into all measurements. You typically also want to take Jupiter's light deflection into account because Jupiter is a very large body also. And you also, interestingly enough, have to take the Earth and the Moon into account, or you should take the Earth and the Moon, because the light deflection is very weak from the Earth and the Moon, but they're very close to Gaia. They're only 1.5 million kilometers away, so you should also take that into account. And of course, then the other planets also have some effect. We actually use the measurements of Gaia. We take all of the measurements of Gaia together and we try to use that to test, does Gaia tell us that Einstein is right, for example? And the point about Gaia is we have so many measurements that we think we can make the most accurate test of light deflection due to general relativity and Einstein's theory and so on possible.
Obviously, it's interesting from the point of view of natural history to make a catalogue of these distances to the stars we see in the night sky. What scientifically can we get out of that catalogue?
Well, first of all, it can give us a detailed map of the structure of our galaxy. As we see it on the night sky, we only have a two-dimensional image of the galaxy, so getting the third dimension is very important for understanding the large-scale structure of our Milky Way. But also the individual distances to the stars are very important to understand their physics. You need to know the distance to a star to translate the brightness on the sky to the real luminosities of the stars and get their physical properties. So all kinds of astronomy will benefit from this information.
Is that structure telling you about how our galaxy formed, how it's evolved, where it's come from?
That is one of the scientific aims of Gaia, to try to understand the history of our galaxy. It is thought that a big galaxy like ours is partly composed of many smaller galaxies that have been eaten up by our galaxy. They have simply fallen into our galaxy. And it may be possible to identify which stars came from different infalling galaxies in the past, and therefore know a little bit of the history of how the galaxy was assembled.
Gaia is going to launch, is it November or December this year? What's happening at the moment?
At the moment, the satellite is going through the flight acceptance review, which means that the engineers and scientists responsible for putting together the satellite check that everything is in order. And it appears that it is there. So it will get the go-ahead for launch in November, December, hopefully.
Gaia is ready to go today. It just has to be shipped to South America and then it's ready for launch. So it has to be flown down in two parts. The sun shield and the spacecraft go separately because the sun shield is so big. And then there's no storage facilities in French Guiana, so it has to be more or less mounted once it gets there and so on and be ready. An Antonov Russian airplane was booked to send it down there in July, and then they were told, no, you can't go. The problem is there was a conflict with some GPS satellites being launched. And because of that conflict, then Gaia got shoved back a little bit. So we've been pushed back by 2 months now till November, December. And there's a launch window in November, December, which is more or less defined by where the moon is, for example. You don't want to launch into the moon. So we have certain dates where we can launch. And we've now been assigned this new launch date from the 17th of November to the 5th of December. And hopefully it'll go then, because the spacecraft is sitting there, all the tests are done. It's really ready to fly. People are just doing some last-minute monitoring of the spacecraft at the moment.
And once it's up, how long until we start getting scientific data back from it?
Yeah, well, the first thing, it has to be sent into a transfer orbit to the L2 Lagrange point, which is 1.5 million kilometers away from the Earth. As it is flying out, the sun shield will be opened. The spacecraft is cooling thermally, so once the sun shield is open, it can actually take measurements. But those measurements will be probably quite poor to begin with, because the thermal cooling of the spacecraft takes a month or so. And also the transfer journey takes a month or so. But people will actually start taking measurements, because the sooner you get something, even though it's very inaccurate, you can start testing your data reduction scheme with it.
When can we expect the first scientific results to come out from that?
Some preliminary results will come already about 2 years after the launch, but that will not be very accurate. So as it accumulates more data and they are processed, we will have successively more accurate results. And the final results, which is what all the astronomers are hoping for, will come around 2021. So there is a long time to wait.
Lennart Lindegren from the Lund Observatory, and we also heard from his colleague David Hobbs. You're listening to The Naked Scientists with Hannah Critchlow and me, Dominic Ford. Down the corridor from Lennart and David, one of the astronomers who's anxiously waiting for their results is Sophia Feltzing, who's working on surveys with ground-based telescopes, which will complement the data which comes back from Gaia. She's hoping to combine the best possible estimates of how old stars are with maps of where they are in the galaxy and how they're moving, to look for groupings of stars that may have a common origin. She told me that while Gaia is very good at measuring how fast stars are moving across the sky, it's not so good at telling us whether stars are moving towards or away from us.
So in order to see how the stars are actually moving in the galaxy in 3D, not just on the sky, we need that third dimension of the velocity. And we can do that from the ground very well. Radial velocities today can detect planets very, very accurately circling around other stars, and the precision there is enormous. So the requirements are easily met by ground-based telescopes and instrumentations that already exist today. However, even if the technology is there, the type of spectrograph you need is not there. You need to be able to take 1,000 spectra in one go, or maybe up to 3,000, covering several square degrees on the sky. So several moons in one go. And you can do that by building new spectrographs.
So you're looking at these spectra and you're working out how fast the star is moving along the line of sight by looking for spectral features which are being redshifted.
That's correct. And we don't call it redshifted when we're looking at stars. We just say that they are shifted in the velocity. I mean, we always talk about redshift because it's the galaxies are moving away from us, but the star could be moving towards you. In the universe, the galaxies are moving apart, but in the galaxy, things are moving in many different ways. So you have a set of spectral features that you will measure how much they change relative to the lab wavelength.
And once you've got this huge catalogue of stars around the sun and how they're moving, what scientifically can you learn from that catalogue?
So the important thing is not just around the sun we're looking anymore. That was the Hipparcos satellite. The Hipparcos satellite is looking, dwarf stars like the solar-like stars is only within 100 parsecs of the sun. Now, Gaia will see sun-like stars 20 times or more further away with equally good precision. So a so-called G-dwarf star, like the sun, will still be very bright in Gaia terms when it is 2,000 parsecs away, which is a quarter of the distance to the galactic center from us. So we can see stars like the sun almost into the galactic center, knowing where they are in the sky and how they move. But that's not the only thing we can get from spectra. So basically what you do is you're splitting the light from the star up into its wavelength. Just like putting a prism in front of a sunbeam, and you see all the colors, is what we do in a spectrograph. But you can do this with very high resolution so that the smallest element you're looking at is really a tiny little bit of an angstrom. Perhaps you've seen how from the sun, if you split up the light in the rainbow colors, there are dark areas in there, dark lines across. And those are absorption lines in the solar spectrum because there are elements like iron, oxygen, and carbon in the outer atmosphere of a star. And each element has its unique fingerprint of such absorption lines. And from these absorption lines, we can calculate how much there is of a given element in a star. And the beauty of the dwarf stars, the solar-like star, is that they live for a very long time and not much happens to them. They're dead boring. For people who like to study how stars behave, how they evolve and things, these stars are not very exciting. They're really actually quite dull. But they're very good because nothing happens in their outer atmospheres at all. I mean, there's nuclear burning going on in the center, but you don't notice it on the surface most of the time. And therefore, if you can measure how much iron, oxygen, carbon, chromium and titanium there is in the outer atmosphere of this star, you have a fair sample of the composition of the gas that this star formed out of.
I guess something you really want to know, though, is how old those stars are, and it must be quite difficult to date them if they're not changing very much.
Right. So, yes, there are many ways of dating stars, but it all has to do with us understanding how stars evolve. And these stars are deemed rather good because there is clear signatures when you put them in certain diagrams where you have the stellar evolutionary model and the temperature and the mass of the star, for example, you can see how old it is. They can be fairly large. Errors on them, it depends really a lot on the exact star. Stars like the sun can be dated within, say, 1 billion years. And the universe is 13 billion years, and the oldest stars we find are at least 10 billion years or something like that. Now, there are more evolved stars, so-called red giants, which you can date very well. And there are 2 satellites, Kourou and Kepler, who are studying very small pieces of the sky. Not like Gaia, who's going to study the whole sky. They are studying particular regions, but they get very good asteroseismology data. So they will be able to age date their stars very, very accurately. And combining those data with the Gaia data, they will also put very strong constraints on the stellar evolutionary models. But we would be happy with very large samples of stars that we can age date within 1 billion years, because then we can see how the larger properties of the galaxy vary as a function of the distance from the galactic center. Not anymore looking at things just near the sun, but how things vary as a distance from the galactic center.
Once you've got this catalogue of where the stars are, how they're moving, and what types of star they are, I guess that's telling you about the history of the Milky Way, when these stars were forming and where.
So the idea is that all of these are bits of a kind of jigsaw puzzle that you're trying to put together. It's a little bit like archaeology, where you're getting pieces of a vase up and you dust them off and you find that they fit together. There might be bits that are missing, but then you can guess what they would look like. So in the past, you see, it has been often like people work on dynamics of the Milky Way or the stars, how they move and why they move like they do, or their ages and their elemental abundances. But we will really truly need to combine this much more. And even if we know what it looks like very close to the sun, within a few hundred light years, and we'll know a little bit what it looks like in the center of the galaxy and out in the halo, we know very little what is in between. And actually Gaia is going to help. When it comes to galactic chemical evolution or galactic evolution, a lot of what we have been inferring has historically been gleaned just from the very, very solar neighborhood, which is a tiny, tiny, tiny piece of the Milky Way and doesn't really tell us about the global properties. Now, when it comes to all this ground-based follow-up, we will need, as I said, to build new instruments, although there are instruments that already can do some of it. So with around 300 other astronomers in Europe, I am part of a project called the Gaia ESO survey. So it's Gaia for Gaia and ESO for European Southern Observatory, which owns and runs in collaborations of 15 different countries, the Paranal Observatory in Chile and the Alma Observatory. And there we are using the FLAMES spectrograph that takes about 100 plus spectra of stars in one go. It's not perfect for this purpose, but it's pretty good. It's looking at a rather small piece of the sky, so we would like something with a bigger field of view. And therefore, the proposal is, and ESO has actually accepted to go forward with this proposal, to build a completely new machine to measure several thousands of spectra in one go. And this is called Foremost and is planned to go on the VISTA survey telescope. Right now, so ESO survey is running. We are aiming at 100,000 stars, and we've already been observing for a year and a half now, and it's going well. We are getting the data analysis underway and starting to write the first papers.
My thanks to Sophia Feltzing from the Lund Observatory.
And thank you, Dominic, for that tour through the universe. You're listening to The Naked Scientists with Dominic Ford and me, Hannah Critchlow.
Now it's time for our question of the week, and Hannah considers the dark side of the universe.
This week, we turn our eyes to the skies to tackle this.
Hi, my name is Daniel Hustard, and I was just wondering, how come dark matter doesn't clump up like into black holes, into singularities, or into sun-shaped objects?
So, after the Big Bang, there was lots of matter around, and gravity plus pressure caused it to clump together to form planets and moons and suns. But how come dark matter doesn't cluster in the same way to form dark suns or dark planets? Or does it? We turn to Dr. Andrew Ponson, cosmologist at University College London.
There's quite a lot to unpack in this question. The first thing to say is that dark matter is this substance that we're pretty sure is out there, shaping the visible contents of the universe. But the dark matter itself is invisible, so we can't see directly what it does. Now, the question itself is getting at the idea of gravitational collapse, which is a critical part of the way that we think the universe has evolved and familiar objects within it were born. Actually, dark matter does undergo gravitational collapse. So you can take an initially large volume of dark matter and shrink it down to something smaller just because of the gravity of the dark matter itself. But the assumptions behind dark matter tell us that, unlike in the case where you have normal gas, the dark matter particles can't get rid of their energy. They continue flying around at very high speeds. Although dark matter particles don't actually feel pressure in quite the same way that normal matter would, you can imagine they're just moving so fast that they can't be concentrated into a small volume. If you tried packing them into a small box, they'd be moving so fast they'd just fly straight out again. So there's actually a limit to how small you can make a cloud of dark matter. You can't make dark matter collapse into a black hole, for instance, because you just can't get rid of the energy to make it that small. And we actually think that typical clouds of dark matter are just the right size to be lurking around galaxies in what we call a dark matter halo.
So dark matter seems to be too high speed to form solid planets, but can form dark matter halos. Well, sticking in space, this time to mine for materials, putting pressure on this.
Hi, my name is Sasha Zanjani from London. Diamonds are made deep underground when carbon is subjected to high pressure and heat. Is there any way that other elements could be used to make an even harder type of diamond? I was thinking of mining on other planets where pressures would be greater due to the planet being more massive.
Thanks, Sasha. So, what do you think?
Hannah Critchlow. And if you think you've got the answer, you can send your thoughts to chris@thenakedscientist.com, tweet @nakedscientists, or join in the debate on our forum, which is at nakedscientist.com/forum. That's it for this week. My thanks to all of our guests and to Hannah Critchlow for joining me. The producer was Kate Lamble. As we speak, Chris Smith is heading down under to Australia to celebrate National Science Week in Perth. And in next week's show, he'll be reporting back to us on the latest Western Australian science. If you're in the area, do get in touch on Facebook or Twitter, and he'd love to see you at one of his science shows. The Naked Scientist comes to you from Cambridge University and is supported by the Wellcome Trust and the EPSRC. I'm Dominic Ford, and thank you for listening. Goodbye.